The question that I have is, could you show us how to solve a 3D cable problem? This is the problem that I have selected here. A mass of 40 kg is being held in space by 3 cables AC, AD and AE and a rod AB. The question is to find the forces in these members. As in early example, the first 2 steps are the same. These are the first 2 steps. First, we want to identify the particles to be analyzed, and in this case, you can see easily those particles are particle A and particle E. Then we go ahead and complete the free body diagrams for these particles, and I have done that on the main picture right here. We have done enough examples at this point to recognize that the force FAE is simply equal to the weight W, right? And therefore, in the next slide, I will only consider the free body diagram of particle A. Now we will apply the equilibrium equations to particle A to solve the problem. The first step is to express each of the 4 forces in their component forms. We recognize that point A is located at the origin of the coordinate system. The coordinates for point B and C are given. And therefore, out of the 3 methods we talked about before, we will use the position vector method in order to express TAB and TAC in their vector forms. On the other hand, direction angles are given for the line AD, and therefore we will use the direction angle method to express TAD in its vector form. So let's go ahead and do TAB and TAC first. First, I list the coordinates for the 3 points that are relevant here, which are points A, B, and C. They come directly from the picture, and I'm pretty sure you can easily follow these. Then I find the vectors representing lines AB and AC and their respective magnitudes. The vector FAB then is magnitude of the vector FAB, which is FAB, multiplied by the unit vector in the direction of line A to B. So let's call that as UAB. But UAB is simply RAB divided by the magnitude of RAB, which is RAB. Now we bring RAB from here and substitute in this equation. Simplify it, we get this expression for the vector FAB. FAC is done in a similar way, we get this for FAC. Now we use the direction angle method to find the vector form of FAD. After simplifying this, we get this for FAD. Finally, this is the vector form of W. Now we apply the equilibrium equations. Here's a summary of what we have done in the previous slide, showing us the vector forms of the 4 forces acting on particle A. Here are the 3 equilibrium equations, the one in the x direction, one in the y direction, and one in the z direction. So what we have is a full-blown 3-dimensional system of equations, each equation containing all 3 unknowns. In other words, we have a 3x3 system of equations. So we're going to have to come up with a 2x2 system of equations and then solve those 2 equations simultaneously to find the 2 unknowns in those 2 equations, and then we go back to one of these 3 equations to find the third one. There are many ways to solve equations like these, and this is what I'm doing here. I'm going to take this equation 1 and divide that by 0.384, which is the coefficient of FAB. So the first term simply becomes minus FAB. The second term will be 0.429 divided by 0.384, which is 1.117 times FAC. And the third term would be minus 0.5 divided by 0.384, which is minus 1.302 times FAD equals 0. I'm going to take the second equation and divide that by 0.767, which is the coefficient of FAB here again, and take the third equation and divide that by 0.511. So that's how I generated these 3 equations. Now I'm going to take equations 4 and 5 and add them together. So when I add them together, these 2 terms will cancel out, right? So FAB disappears from that equation. Similarly, I'm going to take equations 4 and 6 and add them together. FAB will one more time disappear from the equation. So I end up having two equations in two unknowns, which are FAC and FAD. Now you understand why I divided these equations by these coefficients, right? Now we solve these two equations to get values for FAC and FAD, and then go back to equation number 4 to get a value for FAB. So here are the details. Looking at these numbers, we notice that we got positive values for FAD and FAC, but negative value for FAB. Is that possible? Is this a stable system? We marked each of these forces as tensions, right? We got positive values for FAC and FAD, and therefore they are in fact tensions. But we got negative value for FAB, and therefore FAB is actually a compression. But the system is going to be stable because while AC and AD are cables, AB is actually a rod. So a rod can take compressive force.